Mary Martha, you rock. I appreciate you. Hey, we're live with Coach Jay, Coach Jay's class on a Tuesday. No, on a Monday. On a Monday. What's that? Get Gabby and Grant. That'd be good. That'd probably be good. All right? And I put that on the podcast. I would never leave my students in the hallway. This is true. Thank you, Wes. Thank you, sir. Should I give a ticket just because? Sure. I'll take it. I'm coming to you. Gabby and Grant, we just started. This is all review. Okay? All right. As I was saying, X bar and mu are very, very important. Both refer to our mean. The only difference between X bar and mu have to deal with whether it's a statistic or a parameter, whether it involves my sample or whether it's an actual value within my population. So let me give you an example. If I was finding the mean height of everybody in this room, and this was my population, we would use a specific value. We would use mu. Mu stands for my population, okay? Or the size of the jacket you wear, right? And if it was a number, right? Quantitative. I guess that's my size.
Small.
Right?
X.
Appreciate y'all. Love y'all too. Okay? Statistic deals with X bar. So anytime we talk about a sample mean is X bar, whereas mu talks about more of a population, whatever the population is that we define in that moment. Okay? All right. So as we look at this, we will always use a blank to estimate a blank.
Sample population.
Correct. And let's talk in terms of, you're right, Campbell, statistic to estimate a population. Good. Now, what you put down below here, this picture, right? Because you know a sample is a subset of my population. A sample is a smaller version of my population. We talked about ways we do sample, right? We talked about that and how we sample appropriately. That was all in chapter 4 or 5, I forget. But that's what we talked about. Now, remember over here, when we sampled this, we talked about how the true mean of this was 3.53 for crazy in love, okay? Do y'all remember that?
Yeah.
So 3.53 was my, what do we call that?
Your average word.
Which would be mu or X bar?
X bar.
Mu.
It would actually be mu because my population was the one song Crazy in Love, right? Do you remember that? And now I took samples from that, right? And in those samples, I took them out. And within this one, remember the first time I did it, I said, hey, just draw 5 random samples here. Let me do this. Let me look at this. I had this here. Let me see. Is this it here? No? I had it out. Anyway, within that Beyonce activity, remember all those words? And I said just randomly select 5. And it didn't work, did it? Because our mean here, or this was our X bar, was 4.93. When in reality, our population was 3.53. We said that because this was much higher than this one, it displayed what? Bias. Because it either underestimated or overestimated the true mean of the population. Do you remember that?
Yeah.
Okay, good. Now, this is a bad sampling method, right? And this is what I want you to do right here. Just within this picture, put in the bad sampling method or just put something where you have a distribution that has a mean that is much greater or much less than what my true mean is, right? Now, question. What happened when we actually did it appropriately? Y'all remember?
Like 3, 4, 6, 7, something like that.
Yeah, now this was the appropriate method, and I'll put it down below. So the bottom one was inappropriate, where I just said select 5. Mary Martha was right. When we used table D, we actually got 3.21, which was much closer to my true mean, right? So I sampled and got a mean of 3.21. This mean we would call what?
The actual.
X bar, right? Which is a statistic or parameter?
Statistic.
Statistic. Are you getting this?
Mm-hmm.
Okay. What was my parameter?
The 3.5.
3.53, right? Moo moo. So we said, yeah, there you go. Moo mu, right? When we did 10 words instead of 5 words, we actually got closer to our true mean, right? Why did we get closer to our true mean when we increased our sample? Perfect. The larger the sample size, the closer. If we do it appropriately, the closer it gets to my true mean, or mu. Okay? All right, is this connected? This is more of a review. I get it. We'll keep rolling. Okay? All right. When statistics consistently overestimates or underestimates, we say that it is what?
Bias.
Yeah, bias is present. Bias is usually the result of a poor
Sampling.
sample. Good. Good. Y'all rock. How do we try to eliminate the bias in the Beyonce song activity?
More.
More data.
Random more data.
More data,
And the
table D,
calculator,
right?
yeah.
We would say probably a simple random sample, right? Which would be from table D. And I like what you said, Mary Martha. When we have mu, right? How do we get closer to mu? Increase sample size, right? So we'd say closer to mu would be increasing the sample size. For the picture down below, I want you to just put a distribution, maybe similar to this. Doesn't have to be perfect, but just to remind yourself that in this, when we increase this to 10, we got closer to our true population of 3.43. Okay? Is this still X bar? Yes, it is. It's still from our sample. We still say that this is a statistic. Okay? With our parameter as 3.53. Okay? Mu. All right. 2 more, and then I think I've got actually 1 more on the next page, but not very long. A true simple random sample using a digit table eliminated the bias in the sampling distribution. But how can I make a sampling? By the way, is this a sampling distribution?
Mm-hmm.
Why?
You took samples of words within a population.
Yep.
Correct. Here's a hint. This actually technically is not. Okay? We're going to call it a sampling distribution, but to be a true sampling distribution, it's almost impossible. A true sampling distribution would be every type of sample within that population. Is it possible to do that? I mean, it is, but it'd take a long time. So we're just going to call this a sampling distribution, but I just want you to hear that from me, okay? So we're going to call that because it's taking a sample from that population there, okay? But how could I make the sampling distribution even better?
Like we're in every
I
combination.
think we said it, right? Higher sample size. I think Max had that earlier, right? It's good. Higher sample size reduces the blank of the sampling distribution. The bias, what's another word for bias?
Error.
Well, let me do this. Higher sample size doesn't reduce the bias, right? 'Cause that's how
Variance.
the variability, yeah. Nicely done. That's worth 1 there.
Good
Good.
word. Good word.
Does that make sense?
Yeah.
So again, it's not bias, it just reduces the variability of that data. What decreases the bias or eliminates bias?
The table D.
Table D, simple random sample, or through your calculator, right? Depending on how I take
Just make it
that
random.
sample that's there,
Yeah.
okay? All right, last one. What makes a statistic a good estimator of a parameter? So we got our population here. How do I make sure that this sample or statistic is good within my whole parameter?
If it's a sample.
James.
If it's a large enough sample size.
Okay, so we would say yes, which decreases what?
The bias. Variability.
Okay, that's
Or the
one of them,
variability,
but those aren't related. Low bias, which is table D, right? And low what?
Variability.
There you go. Good.
Yeah.
So to get a good
Yeah.
sample, we have low bias and low variability. Okay? Good. All right, real quick. I want you to, for a ticket, let's see if we can talk through this real fast. And then we're going to go to our activity, at least the first part, okay? All right, on Tuesday, the bottles of Arizona iced tea. Any fans? Arizona iced tea?
Gold
Yeah.
pig.
Okay, I hear you. Filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contain an average of 19.6 ounces of iced tea. Man, they're jipping us off. What is mu?
20.
Okay, 20 ounces, and what do we call mu? Mu is the parameter, which is our population, correct? Maddie, could you give me what is 19.6? Statistic and the sample and the X bar, right? All of these things are together. All right, beautimous. Y'all good on that?
Mm-hmm.
All right, let's try this last one. Jerry, I got you on this next one. On New York to Denver flight, 8% of the 125 passengers were selected of random security screening before boarding. According to Transportation Security, 10% of all passengers at this airport are chosen. Could you tell me what is 8% on that, Jerry? Good, it's a statistic. Do we call that X bar or mu? X bar, you're right. Say it confident, you got it. And what is 10%? Parameter, and we call that mu.
Yeah.
Boom,
That's
nicely
my
done.
boy.
Okay? All right, so with that being said, here's what I need you to do. Okay, I'm going to tell you a story, and then we're going to try to do an activity with this, okay? To try to see which of you within your groups can come up with a way to reduce bias for this situation. This is a completely true scenario. This actually happened within World War I, and so I will give this to you, and then we'll go from there, okay? For those that are history buffs, what happened was in World War I, the U.S. did not have at that time drones or anything that could identify the amount of tanks that Germany had within that specific time period. What they found, though, was that in order to kind of identify, hey, how many tanks does Germany have at this time, they had to figure out a way to be able to kind of estimate what the total was for that. So what they did was they captured 5 tanks, 5 German tanks. And when they captured them, they found that the serial numbers indicated from 001 all the way to the highest number or the total number of tanks that they had. Now, on the sheet, the second sheet that I gave you, I want you to take that out, okay, real quick. I want you to look at that. What you see is the numbers of the serial numbers of the ones that they captured from Germany. So they captured one that had a number 21 on it. This was completely random, by the way, completely random. One that had a number of 123, one that had a number of 201, 297, and 342. And so they took these 5 over to statisticians within America and asked the question, based on these 5 numbers, what would be a good estimate for the total number of tanks you would expect Germany to have within this given time period during World War I? So I want you right now, with the group members around you, to try to just talk about the best way you think. There's no wrong answer. I want you to answer, what is your best estimate for the total number of tanks or N? Okay? I'm going to give you 3 minutes to come up with the best strategy of a way that you could take those 5 numbers to think about what you could do with those 5 numbers to get to what you think the total number would be. Ready? Go. World War I is in your hands.
Really twisted my arm on this one.
World War I is in your hands. Here we go.
That would make
Wait.
sense.
We take me with this. Yeah, I don't know. Because to me, it's obviously not going to be wrong. It's obviously going to be
If there's multiple results, it could be the same, so there can be like 2, 2, 1. So that's multiple 2.
I'm guessing that
There's only 1, 2, 1.
to add,
What is
I'm
it?
guessing that's not add the same.
196, 197. Add that to 332.
Good to go.
539.
Good, yeah, there's no wrong answer on this one. So there's no wrong answer.
I would think some deviation.
That's our estimate.
We're just guessing. A little bit. Right here.
Remove, that's the actual total number.
What was the best idea?
To estimate a population.
How do we know what the best idea is?
We estimated the whole population.
Yeah.
Alright,
So we're trying to see.
we should use to find the,
I just want you
we
to.
found of the subs, add a big number, simple words.
We do something with I mean, the most basic way is what? Take the mean or the middle, and then we know that that's 50%.
And then we added it
We can multiply that by
Yeah.
2 to get to where we're at. Now, that would be a basic example. But that's really so stuff like that would be something that you just come up with one rule that you think,
Yeah.
you know what, I'm gonna go with this. Got it? Sound good?
So those are our samples.
What'd y'all come up with?
539.
Up there, how'd you get it?
We found the mean and added it to the big number,
Okay,
342.
gotcha.
Because they were still increasing by a lot, so we knew that there still had to be, like, there was a lot of variance in this mean, so we knew there was gonna be a big one.
Cool. I like it.
Closer, but is that semi?
I mean,
Yeah,
there's no wrong answer here.
yeah.
No,
okay.
says that.
How'd you do it?
No, they had the mean.
We're about to find out how the PhD exam did it.
So there's no like, oh, I got it. I just want you to think about
This class.
those 5 numbers to guess what my.
Oh, heck, fine, I can barely count.
Yeah, I like that.
Yeah, I was doing it.
That's my best guess.
It's good enough.
What else?
I'm just gonna.
Yeah,
We
so
got
based
the
upon
gist.
that, if that's a random thing.
There's a lot of that.
Those 5 numbers to kind of come up with a pretty good estimate.
Just little ones.
You could do a regression, that's a really good, but I think that's more complex than we're trying to get to.
What's the number?
It's a marathon.
$1 billion.
Okay.
Oh, I won't have
I like it, yeah, I would just come up with the rule, right, for instance, take the mean, which is the middle number, that's the 50%, and multiply the 50% by what? By 2 to get you what you need. Something like that would be an example, doesn't have to be that way, but it could be. Does that make sense? Okay? Is anyone confused right now? What y'all?
Yeah,
No, ours is better.
Okay, so you have you said the standard deviation was there. Gotcha. Perfect. Add it to the top number. Perfect. Okay,
I feel like you would.
here's what we're gonna do. Okay? Did y'all come up with a rule, kind of, sort of? Right?
Yeah.
Okay. All right. Hey, listen, real quick up here. Okay? We're gonna see whose idea is better. Okay? Whose idea is better? So we have 4 groups, right? We have 4 groups. So what we're gonna do is this, just so that everyone's on the same page. There is, and some of you are like looking at me like, Coach, are you trying to get the best idea? There's no good, better, best. What we're trying to do is see which is the best group. We can determine who is the best group because guess what? If X bar is closest to what my true parameter is, the team that comes the closest, that's the team that that's the team that wins or has the best rule. Okay?
But there's
no wrong and will save us from Germany. So thank you very much. Real quick, guys, just real quick, could you all just explain what your rule is? Get these down below.
Add the standard deviation to the top number or the highest number.
Add standard deviation of these numbers to the top or highest number. Okay? That's rule 1. Guys, you're going to be using that in just a second. I'll show you why in a second here. Number 2, what do we get, Campbell?
We took the mean of those 5 and added it to the highest number.
Mean and add to high number, or max, you could say. Perfect. That's rule number 2. Y'all are going to execute that in a second. Morgan, did y'all figure it out on number 3?
We did the one that you said.
Okay, give it to me.
Find the mean and then multiply it by 2.
Find the mean and multiply by 2. Okay, I like it. I like it. Jerry, did y'all get one? Emily, did y'all get one?
But you help us.
Find the range. Okay, so I take the range, which is the highest minus the low, and just get that number there. Times 2. That's fine. I'm good with that. That's fine. There's no wrong answer. So number 4, find range and multiply by 2. Okay? All right, here we go. You ready? Next part.
What's yours?
Yeah, we have a
Doesn't
fifth
matter what I
spot.
say. Doesn't matter what I say.
What do you think?
Okay. So these are all of these. The 5 other rules that could be used to estimate the number of tanks include the following. So these are the ones that could be used.
Wrote those down.
You could write these down. These are again some of the ones that you said were decent. I like how we're thinking there.
Solid.
No, I do. I like
They were
it.
decent, guys. Good job. Yeah.
Okay. So the ones that I would say that I included, or the ones that were used there, were to double the mean. We had that one. Okay. 6 times the standard deviation.
Why?
How many standard deviations to the left and right of the mean do you normally have?
3.
Mhm.
Alright.
That's what.
That won't get you all of them.
99
No,
point-
that'll get you 99.7.
True, but we're just guessing. We're just guesstimating. Someone said 4 times the standard deviation. Okay. 2 times the median. Okay. Another one that was said, max plus min. Max plus the min. And last is 3rd quartile plus 1 standard deviation.
Oh.
3rd quartile plus 1 standard deviation. Okay? So here's the thing. Maybe you like your idea. Maybe you don't like your idea very well. By the way, question. This big N, is that a statistic or a parameter? Parameter. Good. I want you to circle that. Okay? Now, what makes a statistic a good one? What do we say?
No bias and variability.
Low bias and variability. Now, what we're going to do is we're going to test to see whose is the best. Now, if you don't like your idea or you think, man, one of these looks better up here, I want you to identify with me that change, and you can go ahead and execute that yourself, okay? Now, how can we see which one gives the best estimate?
More reps.
Reps, good, and the one that has what?
The close or the least bias.